Hello, dear students. Today we are going to see chapter 14 that is about liquids and solids. Well, we have studied already the gas, and today we are going to see the liquid and the solid. As you can see, the gases has a low density and they are very compressible and they can fill a container. So no volume and no um, shape uh, is fixed. It depends on the volume of the container. The liquid, they have a volume, but the shape depends on the vessel they are. The solids has both fixed uh, volume and shape. And here is the water heating cooling curve. I want you to see that this curve has in the y-axis the temperature, while you have in the x the heat that is added every certain time. As you can see, the temperature remains constant while there is a change of a state from the solid to the liquid. The temperature is constant. And the same happens during the change of phase between a liquid state and the gas state. This curve can study the heating or the cooling process. The normal boiling point at 1 atmosphere is 100 Celsius, while the normal freezing point at 1 atmosphere is 0 Celsius degree. The density of water in the liquid state is 1 gram per milliliter, while the density of the ice is lower. The, the problem that the density of ice, the solid, is lower than the liquid is anomalous. And the reason why we have this anomalous behavior is because of the hydrogen bonds between the water molecules in the liquid state. Here we have a question. During the process of melting ice by adding heat, what would happen to the temperature of the ice? Well, during the change of the state, that is a physical change, by the way, because we continue having water molecules, the temperature remains constant, as you can see here. As I told you before, the changes of states are physical changes because no chemical bonds are broken. When water is boiled to form steam, water molecules are separated from each other, but the individual molecules remain intact. Phase changes. When a substance undergoes changes in the state from solid to liquid and from liquid to gas, the molecules remain constant. Then all these changes are physical because the water molecule remains the same in the three states. It's the same kind of substance. And during the change from the solid to the liquid, as energy is added, the motion of the molecule increases because in the solid state they are fixed in one place. But when they goes into the liquid state, the molecules are not in fixed position. The molecules can move freely. And then when you go into the gas state, the molecules are so apart one from the other that they can move randomly. The water molecules have intermolecular interactions that are known hydrogen bonds. Uh, First, we have in the molecule the covalent bonds between carbon and hydrogen, and intermolecules, we have the uh, weaker hydrogen bonds. Then always the hydrogen bonds, the intermolecular forces are weaker than the covalent bonds that make stable this structure and contains highest levels of energy. Here you have, for example, the hydrogen bonds that are very weak if we compare with the intramolecular bonds. Well, the molar heat of fusion is the energy required to melt 1 mole of a substance. And the molar heat of vaporization is the energy required to change 1 mole of a liquid to X vapor. Here we have an example. What is the amount of heat that we need for certain amount of substance? You can stop the video and you can see this sample. Which is the stronger intramolecular forces or intermolecular forces? Okay, I already answered it, but you can stop the video and you can read here and you have the answer. Which you could predict should be larger for a given substance, the enthalpy of vaporization or the enthalpy of fusion? Well, the answer is that the enthalpy of vaporization is always higher. Why? Because the molecules are still relatively close and interact in the liquid phase. And in the gas phase, the molecules are far apart, and these intermolecular forces are very, very small. Therefore, more energy is needed to break these forces completely during vaporization compared to just partially during fusion. Here you have another question. You have already the answer, and you have the answer here given. Just stop the video and you can see it. Intermolecular forces, forces that occur between molecules. We have two types, the dipole forces, and in this case we have the hydrogen bonding, that is one of these type of forces, and the London forces that are typical of molecules that are not polar, even though polar molecules also can have London dispersion forces, but they are very weak if we compare, for example, with hydrogen bonding. The dipole attraction into two poles. Look at here. You have here the interaction between the positive and the negative part of two different molecules. And here you have the interaction of many dipoles in a liquid. The dipole moment molecules with polar bonds often behave in an electrical field as if they had a center of positive charge and a center of negative charge. The molecules with dipole moments can attract each other electrostatically. They line up so that the positive and negative ends are close to each other, only about 1% as strong as covalent or ionic bonds. Then, as you can see, the dipole forces are very, very weak in comparison with the strength of covalent or ionic bonds. The hadron bonds are strong dipole forces that happens between molecules when hydrogen is bound to a high electronegative atom like nitrogen, oxygen, or fluorine. Then only when hydrogen is attached to one of these three atoms, we can have hydrogen bonds. And these bonds are intermoleculars, are stronger than the dipole forces. And of course, the hydrogen bonds are weaker than the intramolecular forces in the bond, like the covalent bond and the ionic bond. Here you can see that the hydrogen has a positive charge or partial positive charge, while the oxygen is more electronegative. And then there is an interaction between the positive part of one molecule and the negative part of the other molecule. That's what we call hydrogen bonds, and only happens when hydrogen is attached to oxygen, nitrogen, or fluorine. And this is the answer why water is at room temperature a liquid, while similar molecules are gases. And that's why the boiling point of water is so high. It's because of the hydrogen bonds that are extra bonds that are needed to be broken, and then you require a higher energy to break down molecules apart. The London forces are forces that exist among, for example, noble gases. They are non-polar molecules. Then, because of the movement of the electrons, in certain times, you can have more density of electrons in one side, and then there is an instantaneous dipole. And then that's why it can happen the interaction with another atom. Significant, significant in large atoms and molecules. When the molecules and atoms are larger, then it's more probable to have these London dispersion forces. The London dispersion forces are characteristic of non-polar molecules. When we have non-polar molecules, when the atoms in the bond are the same, then there is no difference of electronegativity, and there is not a dipole. Only happens an instantaneous dipole in the molecule. You can see here that in this table become stronger as the size of the atoms and the molecules increases. Then the bigger the molecules and atoms are, the more probably you will find a stronger London dispersion forces. And the same thing, that's why the stronger intermolecular forces like hydrogen bonds presents higher melting and boiling points. Here you have a question, already you have the answer, so stop the video and you can see the answer. Here you have another one. Well, in this case, I will help you. These molecules, this kind of molecule cannot have hydrogen bonds because an spherical um, situation. But in this case, you can have a positive and a negative part in the molecule, and then they can interact with other similar molecules. Which gas would behave more ideal? Well, in the same condition, nitrogen is covalent nonpolar. So the interaction between molecules are almost null. There are not almost interaction. While in carbon monoxide, this molecule is polar, so there are interactions between molecules. That's why the covalent nonpolar, there are almost no interaction and more molecules, and then the behavior is more ideal. Here you have another question. Consider the following compounds. How many of these compounds above exhibit exhibit London dispersion forces? The three can. Any molecule, any atom can present London forces because they can make an instantaneous dipole. Vaporization or evaporization. Molecules of a liquid can escape from the liquid surface in form of gas. The endothermic is an endothermic process because it requires energy to overcome the relatively strong intermolecular forces in the liquid. The vapor pressure amount of liquid decreases initially. The amount of liquid decreases initially and then becomes constantly. The condensation process by which vapor molecules convert into liquid when no further change is visible, the opposite processes balance each other. Then at certain time, the the amount of molecules when it's a closed system that goes into the gas and the amount of molecules that goes into the liquid are at equilibrium. Then we get the equilibrium and almost there are no change visible. The, the equilibrium vapor pressure is the pressure of the vapor present at equilibrium. The system is at equilibrium when no change occurs in the amount of liquid or vapor because the two opposite processes exactly balance each other. Well, we have a question. You have already the answer here. Then you start the video. You have here another question. The liquids in which the intermolecular forces are strong have relatively low vapor pressure. Well, here you have, for example, in the vacuum, this is the 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 pressure, as you can see here. But for example, in water, that you have more interaction, the pressure of vapor is different from this molecule diethyl ether vapor, where you have less interactions than in, or weaker interactions than in the water molecule. Then in diethyl ether, that is much more volatile than water and thus shows a higher vapor pressure. In this case, the mercury level has been pushed down to this value. So the vapor pressure of diethyl ether is 545 millimeters of mercury at the same temperature. Here you have a question, you have the answer. Well, crystalline solids are those ones where the atoms, molecules, or the ions, for example, are in fixed position in the space. That's a crystalline solid. The crystalline solid can be divided into ionic solids. The components are ions, or molecular solids, where the components are molecules, or atomic solids, where the components are atoms. The ionic solids, ions are at the points of a lattice. And in molecular solids, they are discrete covalent bonded molecules in each of its lattice points. And in atomic solids, atoms at the lattice points that describe the structure of the solid. Here you have three examples of um, solids. Here you have the diamond, here you have the sodium chloride, and here you have ice. In this case, diamond is made of carbon. They are um, atoms. Sodium chloride is an ionic compound and it has two ions, sodium and chlorine. And ice is made of molecules. They are polar molecules. And then you can find in ice the water molecules in fixed spaces in the solid. Here you have in this table different kinds of solids that and what are the units in each case. The ionic solids are very stable substances with high melting points because between one cation and one anion are electrostatic forces that maintain the particles at very close, and you need a high energy in order to break down these bonds. That's why the melting point of sodium chloride, for example, is very, very high. But, for example, here you have the molecular solids. You have molecules in the solid. They melt at low temperature and they're held together by weak intermolecular forces. In atomic solids, you can have, for example, atoms of the group 8 noble gases. They have low melting points, but for example, you have the diamond that has a very high melting point. Here we have the metallic bond. The metallic bond, the cations are in fixed spaces into the solid, while the valence electrons are free electrons and they move in a cloud around this structure made by the cations. And let me tell you that um, this structure is very important because these free electrons that are in the cloud can conduct electricity and heat. That's why the metallic bond has special properties. Here you have some bondings in metal, for example, when you have alloys, one metal, for example, zinc can occupy spaces that were occupied before by copper. And also you have in the holes among the cations or the of the metal, in this case of iron, you can have in the interstitial places you can have, for example, carbon. This is steel. Steel is an, an alloy between carbon and iron. Well, that's all for today. I hope that now you have a better idea about the characteristics of liquids and solids. See you soon.